But today we have two marvelous speakers who have contributed in the most fundamental ways to mathematics, but in somewhat different ways. Both are British mathematicians, and I'll spend my time this morning maybe talking more about Robert Calderbank. Robert started off in Warwick. He was profoundly and deeply influenced by Peter Cameron before going to the United States. And if you're looking for impact of that kind of research, of the information theory and so on at the time, it's hard to imagine that modems would be the same as they are today, that our mobile phones would be the same as they are today, or indeed that Bell/Lucent research labs would be the same as they are today, had it not been for Robert Calderbank, his scientific contributions and his leadership contributions in making mathematics count. And I don't want to spend any more time on it. I think we're extraordinarily privileged to have him here today, and he's going to talk to us about the art of measurement. Robert.
Well, I'd like to thank Terry for an extraordinarily generous introduction, one that I'm not at all sure that I'm going to be able to live up to. I'll just elaborate a little bit on what he said. I mean, as he said, I'm a mathematician. All of my degrees are in mathematics. I have made my living hanging out with engineers. First at Bell Labs, then other places. And what I do is I make a bet, which is that if I listen to engineers long enough, then I will discover something that I can do that they can't. And so those of you in the audience who are old enough to remember these modems that burped and squeaked at you, those have everything to do with finite dimensional lattices like E8 and other lattices. When you use your mobile phone and it talks to a base station with more than one antenna, so if you look up at these poles and you see more than one antenna, you're actually using an instantiation of the quaternions as a 2-by-2 matrix. And these are examples of mathematical quantities that I'm not sure engineers would have gravitated to by themselves. So that's how I make my living. I'm at Duke University. I'm a professor of mathematics and electrical engineering, and I run something called the Information Initiative at Duke. And I can say that one of the benefits of having senior university administration that are all humanists is that they don't realize that the acronym for your institution is a pun until much, much later. Anyway, I should like to start by acknowledging my collaborators, particularly Matt Nokleby, who was a graduate student at Rice in wireless communication and came to Duke to change fields. We together made a bet that what we both knew about communication theory could say something about machine learning, and that's the subject of today's talk. And I'm happy to say that it's sort of paid off for him, because he's just got a job. So he's feeling very good about this decision. Ahmad Bahrami is just starting his graduate studies, and Miguel Rodriguez is someone who I started to work with when he was a professor in Portugal, and now he's moved to University College London. Okay, machine learning. This is about automatic classification. So here in June 2012, Google trolled through millions and millions of YouTube videos. And what they were trying to do was to automatically segment that corpus. As they did that, what they discovered was that one of the keys to segmentation was to be able to distinguish which videos involved cats, because an awful lot of internet videos involve cats. And so this was reported in the newspapers as developing a neuron for detecting cats. And you can see a picture of the neuron here. Not to be outdone, in 2014, Facebook unveiled something called Deep Face. And what Facebook did was they looked through for some million Facebook images. And they used those images to build features that could distinguish one face from another. And then, having discovered these features, they turned them loose on celebrity faces in the wild. And they reported an accuracy rate of 97.25%, which is only very slightly worse than what humans are able to do on their own. This is clearly one of the crowning achievements of our civilization. Final slide. This is a picture of Jeff Hinton, who is smiling very broadly. And the reason he's smiling is that his company, DNN Research, has just been acquired by Google. And Jeff is a researcher who's been at the forefront of neural networks since the 1980s. He's a pioneer of deep learning. And the first question that I'm going to look at in this talk is whether there's something that Jeff couldn't do, even if we gave him a bigger computer than he could ever imagine. So are there mathematical things that are inaccessible? So today's talk, we're going to talk about, if you like, two phases in machine learning. The first is the training phase, where we look at a whole bunch of training samples, and we try and distinguish features. So here we're trying to distinguish human beings from cats. And this is a picture of our neuron for each one. After we've trained, we classify. So we have test data, and the job of the classifier is to assign labels. Is it a human? Is it a cat? Now, in the training piece of the talk, which is going to be at the end, we're going to think about how much training do we really need. So the first example used 10 million training images, and DeepFace used 4 million labeled images. How much training is really necessary? I mean, in some sense, if you're Google or if you're Facebook, the best answer from their point of view is that you need lots and lots and lots, because then only they can do it. But the question is, how much do you really need? And so we have an intuition that the more training samples we have, the better we're going to be able to do at classification. So we in a sense intuit the broad shape of this boundary, but we'd like to give it some mathematical substance. On the classification side, raw images are expensive. They're big, they're hard to manipulate. We'd like to make them smaller. We'd like to compress them. And we'd like to be able to do just as well with the compressed images as we could with the originals. So how far can we compress data and still obtain the same fidelity? Again, as we increase the fidelity of representation, we ought to be able to distinguish more things, so we have an intuition about how that boundary should behave. we'd like to give that more mathematical substance. So there's going to be two pieces to the talk, and then there's going to be a third piece sandwiched in the middle. So we're going to look at subspace classification, and then we're going to look at how much training do we need. So here what I'm going to try and do is to motivate subspaces for you. So our signals, our classes, are going to involve subspaces. Why subspaces? Well, if you see at the bottom of the page, there's this reference to a paper by Basri and Jacob. And so these are people in computer vision, and what they were doing was they were looking at imaging convex bodies. And so what is an image? What is it to image a convex body? Well, think about light coming from the far distance. So you can think of a pattern of intensities on the surface of a sphere. So that's the imaging, that's the illumination. And then there's a model here, Lambertian reflectance, which means that when you make the image, which is also going to be intensities on the sphere, it's just given by the normal from the convex body to the sphere. So imaging is a mapping from one set of illumination on the sphere to a second set. And what these guys discovered was that if you look at that map in the right basis, and the right basis is spherical harmonics, then it's essentially a 21-dimensional map. And an individual convex body is a 9-dimensional subspace. That's an amazing thing. So that's part of my motivation for subspaces. Now, I must say that this is only approximate. I mean, if you looked at yourself in the mirror this morning, you will have noticed that you had a nose. And so you are not quite a convex body. So with the exception of Voldemort, this is an inexact model. Anyway, that's motivation. So we have the subspace model. We're actually going to have affine subspaces, so they're characterized by a mean vector. That's just the mean of the image, and basis for the subspace, which we'll just think of. The basis vectors live in an n-dimensional ambient space, and we think of different faces as corresponding to different subspaces. Now, we're going to compress our images. So now I'll take you through a sequence of 3 things, maybe 4 things. So what I'm trying to show here is that maybe I should have made the matrix different dimensions. What I'm trying to show is that as you make M smaller, as you project into smaller dimensions, then you get fuzzier features. If I think of those features in terms of subspaces, those subspaces, they're getting closer together. And so when I get here, they're much harder to tell apart than they were before. So there are fewer measurements, they're harder to classify. And I want to think of a mathematical model that captures that. So, because I'm a communication theorist, I'm going to want to bring in a notion of noise. So what is noise in this environment? Well, I have a model subspace, and I have images that are supposed to fit this model subspace, but they don't do so exactly. They do project onto the subspace, And I'm going to think of the energy in that projection as the energy of the signal. But there's also a residual, and that residual has energy too. So I'm going to think about noise, not in the usual way, but as the mismatch between the true world and the model that you have of the world. And my message is going to be that you can't avoid this model mismatch. So even if Jeff has an enormous computer, he can't avoid it. And once you have noise, once you have model mismatch, there are fundamental limits on how well you can do. So we're going to take these measurements. This matrix phi, which is often taken to be random Gaussians, things like that. It takes the subspaces in the bigger space and it projects them into the smaller space. And the classifier tries to tell the projections apart, tries to tell them apart in the presence of this noise. So we have a notion of average error probability. We have a theorem. And what the theorem says, so L here is the number of classes. So log L, that's just the exponent, mod 2. And you see that this expression involves the noise, sigma squared, and and also M, which is the dimension of the space that you project onto, and K, the dimension of the original feature. So this matrix phi that we choose, it's not going to kill any of the content in the original k-dimensional subspace. It's going to just take you into a k-dimensional subspace in the m-dimensional space. And I'm not going to have slides that talk to the proof very much. I'll just say that the only if part of this is an application of Fano's inequality, which relates information that's lost on a noisy channel to classification error. And the if part, you look at where things go wrong when you try to tell one subspace apart from another. That's given by something called the Bhattacharya bound. And then you do a union bound argument on top of that. So those are technically how this theorem comes apart. What I'd like to do instead, instead of going through the proof, is to just give you some intuition about how it relates to the well-known formula for Shannon capacity on a channel. So how does this duality with communications work? Well, here in communications, you have a code book. You have some binary vectors that you're sending over a binary symmetric channel, which sometimes turns zeros into ones and ones into zeros. And you decided that you were going to send that green one. That's what you did. But the channel screwed it up a little bit, and that's what you actually receive. And what the receiver does is it tries to, it knows what the code book is, and it tries to find the code word in the code book that most resembles the vector that was received, and that's what it decodes. And so the important thing here is not to think about this channel as passing bits, but to think of the channel as passing hypotheses, the hypothesis that a certain code word was sent. And the receiver, it's trying to decipher these hypotheses. So here, what Shannon capacity is you're maximizing the mutual information between what was sent given what you receive. And you can think of the capacity as the log of the number of code words divided by the code word length, given that you can drive the probability of error to 0. Now let's think about what we're doing, classification. Well, we have some hypothesis. This is our face. After we make our measurements, this is what we receive. The classifier tries to figure out which one of the images we got, decides on that. Again, we have a notion of capacity, which is the log of the number of subspaces divided by the number of measurements, given that you can send the probability of error to 0. If I wanted to describe that in terms of mutual information, what I would say is that what does it mean to have tried for a certain capacity rho and to have fallen short? Well, what it means is that the mutual information between what you got and your class is less than rho, no matter what kind of miracles you try to pull off by choosing the sensing matrix phi. And capacity is an infimum because it's when you stop failing. So that's the duality between the two. And if you think about these two formulas, if you think about a k-dimensional subspace in an m-dimensional space as having m minus k degrees of freedom, that's like the W in the Shannon formula. So you can think about the bandwidth as being m minus k over 2 hertz. So that gives you some feeling for that quantity. And now we've done the first part of the talk, which is to say something about this boundary. So we have some notion of mismatch between the true world and the model that you have of the world. And the boundary between what's infeasible and what's feasible is given in this way. We can do a little, there you go. The moral of this slide is that when you have exponential growth, there's a lot of value in making a small number of extra measurements. Now, what about real-world data? So here's a very little experiment. So the Yale B face database has 38 subjects, each of which produces 64 images under different lighting conditions. And what we wanted to do was to look at taking different numbers of measurements and seeing if we could see this a phase transition which showed capacity. So here we're somewhere between 4 and the population of Birmingham. So 38 is closer to 4 than the population of Birmingham. But you can see that the performance agrees with the theory in the sense that there is a phase transition. It doesn't happen as abruptly as perhaps we might like. We think that that's because the subspace model is far from, is not exact. There's a tail and the tail matters. But still, it is consistent with our picture. Okay. Now, so that's the first part of the talk. Now there's a little bit in the middle, which is about how do you design measurements? So this is a representation of the MNIST database, which is just handwritten digits. There are 60,000 training examples, and there are 10,000 test samples, and this is a data set that's curated by Jan LeCun and Corinna Cortez and Chris Burgess, and it's been the basis for many machine learning investigations. And the question that we want to ask is, suppose I wanted to tell which one of these digits I had, and I only had one measurement. What would that measurement be, and how would I find it? If I had two measurements, what would they be? How would I find them? And this part of the talk has a mathematical moral too. I have a colleague, Larry Karen, who gave an undergraduate course on signal processing to first-year students. And he taught them things like how to organize their iPad, how to organize the songs on their iPod according to chords, things like that. And some months later, he was talking to Rafi Kaufman at Yale, and he was apologizing for this course. He said, you know, Rafi says, I think the only thing that I really did in this course was the SVD. And Rafi looked at him and he said, what else is there? And so the moral of this part of the talk is that the SVD is really a useful thing. So, having set up the SVD in that way, what we're going to try and reason about is, how should I design a measurement matrix? And what I'm going to do is I'm going to design the measurement matrix in three parts. So I'm going to think about the left eigenvectors and the right eigenvectors and the diagonal stuff in the middle. And I'm going to think about what's the purpose of each of those things. All right, so here we have, this is what we measure, y equals phi x plus n. And our measurement matrix phi, how does it relate to the covariance matrix, sigma n, of the noise, and the covariance matrix, sigma x, of the signal? So let's take the SVD of those two matrices, take the SVD of sigma x and the SVD of sigma n. So that has eigenvectors eigenvectors ux and un. And I claim that the right choice for the left and right eigenvectors of phi is un and ux. Now, why is that? What is the purpose of ux? So the purpose of ux, which is on the right-hand side of phi, the purpose of ux is to gather energy from x. And the best way to gather energy is to use the eigenvectors of the covariance matrix of x. So that's why that's there. What's the role of the left eigenvectors of phi? Well, what phi is doing is it's taking in high energy modes and it's mapping them against low noise modes. So the left eigenvectors of phi, those should be the eigenvectors of the noise process. And so what we're going to do is we're going to organize the singular values of x in decreasing order. And we're going to organize the singular values of sigma x in increasing order so that the high noise modes go, so that the high energy modes go with the low noise nodes, so that if we look at the relationship between noise over signal energy, that's increasing. So we have a picture that looks a little bit like this. So here we've got noise over signal, and it's increasing as we go down the modes. Now, when you look at this quantity, obviously you can do better and better by increasing the energy of phi. So you have to put a bound on the extent to which you're allowed to magnify energy. And if you think of that as water, what you do is you make this picture and you fill it with water. And the height of the water here tells you what the diagonal elements of the SVD are. So where you have a good channel, like channel 1, you want to invest a lot of power in that channel. And when you have a crappier channel, like 3, you don't want to invest quite as much. And that intuition is obvious here. Now, all right, so there we go. That's that. Now, water filling is an old idea in information theory. This equation enters into all sorts of communication problems. So in communications, often you have a source X, and you have a channel phi, and you're trying to get your source X through the channel phi. So you're trying to build some kind of pre-filter. And you build pre-filters by aligning SVDs. And that's, when we're making measurements here in machine learning, that's what we do. What I showed you here was for Gaussian signal models. Now, Gaussian signal models are actually very useful. I mean, if you think about speech synthesis, if you think about how your mobile phone works, what we do there with speech synthesis is we first of all make a linear model of your vocal tract, and then we exercise that model with Gaussian noise. So that's like a subspace model exercised by Gaussian noise. So Gaussian sources are pretty much ubiquitous. But of course, there are more general sources. And then the theory for the Gaussian sources has to get augmented a little bit. And it's augmented by the augmentation uses the MMSE matrix, which is really all about the gap between Gaussian and non-Gaussian processes. And I can, well, maybe I won't do that. The interesting thing from from information theory point of view is that if you think about the mutual information between the class label and the measurement, and you think about its gradient, there's a beautiful result by Sergio Verdu and Shlomo Shammai and Dongming Guo that the gradient of the mutual information is the MMSE matrix. And so if you want to know what's the best measurement or what's the best batch of measurements, you can figure that out by doing gradient descent. And that's what we did. So Sergio has a beautiful series of papers. The first paper on Gaussian sources, the second paper on non-Gaussian sources, where instead of water filling, he does something called mercury water filling, where before he water fills, he pours mercury on top of those top of those little. He puts a layer of mercury on top of here, which has to do with the difference between the distribution he has and a Gaussian distribution. So that's... So now, in the final part of the talk, I'd like to talk about subspace classification. That is to say, how much training do you really need? So here again, we feel that the better the fidelity of our representation, the more things we're going to be able to tell apart. But we'd like to get some more clarity about the form, the mathematical form of this boundary. So this is what we got for subspaces, classification, and we'd like to do the same here for training. And we're going to make a connection to rate distortion theory. I'll tell you a little bit about what that is. So here, we know that when we have too few samples, in a very complicated model, we tend to overfit and model noise rather than the structure of our problem. If you have enough data, you can use all the data you have, but we'd like to have an idea of how much we need. All right. Now, here I'm going to skate over classical machine learning. So in classical machine learning, there's something called the Vapnik-Chervonenkis dimension, which measures the flexibility of a classifier family. How flexible is the classifier family at describing sets, classes? So there's this notion of shattering. So here, this picture, where our classifier family is straight lines in two-dimensional space. We've got 3 points. And we observe that from our classifier family, that is, from our family of straight lines, we can produce any possible division of these 3 points into classes. So we can label them plus or minus 1 in any one of the 8 possible ways. So this classifier family shatters any set of 3 points in the plane. Now, of course, there are sets of 4 points that it doesn't shatter, because if you have 4 points and you divide them into 2 pairs, and those 2 pairs have intersecting convex holes, then it doesn't work. So there is, in statistical learning theory, there's this notion of VC dimension, which is based on this measure of how flexible your classifier set is. And it's really this notion of dimension is of great theoretical consequence in machine learning. It is, however, a little bit loose when it comes to predictiveness. So this is the bound. So the error bar, that's how well you did on your training set. And you want to predict how well you do on your test set. And you can see here that the VC dimension H plays a key role. Now here, of course, you have to have more samples than the dimension. And the dimension can be large. Now, these bounds are usually very pessimistic. And so we'd like to think about whether we could do better by asking a slightly different question. So here, we're going to be looking at these signals of interest, and they have a label L. It's going to look at binary things. And we're going to think that there's a parametric model in the background. So this alpha, it's like packing and covering. So alpha is a way of parameterizing space. How could you think about that? Well, if we went back to the MNIST database, right, where we're trying to tell these classes apart, what could this model alpha be? Well, you could think that each of these images of a digit, you could make them 0, 1, and you could think that some of these numbers involve a little bit more ink than other numbers. So you could think of a digit as being a realization of a binary vector, and the binary vector being driven by a Bernoulli prior, and these Bernoulli priors would be different. So that's an example of a parameterization of space. You don't actually know what those rates are. You just know that there is a parameterization that covers the space. So that's the... And we're going to want to understand predictive value in terms of that parameter D, rather than in terms of the VC dimension H. So here, very simple example. We could think about a pair of Gaussians centered at alpha and minus alpha. We don't know alpha. We do get training samples. So there is, of course, an ideal hyperplane, which is shown in black. But we might look at the training samples and we might infer the more brownish hyperplane. So we would like to understand the relative performance of the classifier we learned versus the best one. So I'm thinking about this maximum a posteriori classifier W. This is a very complicated object. It might require many bits to describe it. We built this classifier Q with fewer bits. So W is a relatively high rate process, and Q is a relatively low rate process. So there's a gap between the two. And if we were to run them both on test samples, there'd be a difference in performance. So there'd be some distortion that we would incur by using the lower rate classifier. So we'd like to understand that a little more. So here's the theorem. H of W is the entropy of the best possible classifier. This mutual information term here at the bottom, which comes out as d over 2 log t, t is the number of training samples, plus an O of 1 term. This is something that comes from universal compression. So you have some source that you're trying to learn. How well do you learn it with how many samples? The O of 1 term is related to Fisher information of W, and you have to be careful about it. When you work it all through, the distortion, the difference between the best possible classifier and the one that you learned, is around square root of d over t. D is the dimension of this parameterization space. T is the number of samples. So D here is playing the role of H in the VC theory. Let me say a little bit. So how do we understand this this variation between W and Q, let me again appeal to communications. So suppose that you had a random memoryless source, rate 1/2. Suppose you had an suppose you're flipping equiprobable zeros and ones, but you're not encoding it at full rate, you're encoding it at rate 1/2. So you have an ensemble of code words, and every time you generate an equiprobable string, you find the nearest code word and you ask, how many bits did you have to change? If you take something like the famous Golay code, which is a code of length 24 and dimension 12, you can show quite easily that any binary vector of length 24 is within 4 bits of a Golay code word. 4 over 24 is 1 over 6, so you would have to change 1 bit in 6. So that's the distortion. And in the communication theory literature, there's a theory of rate distortion. For bits, for the Hamming metric, it's particularly simple. This region is given by 1 minus h of d, where that's just the entropy of the source. And if you were to compress at rate 1/2, you'd find 1/6 in the feasible region. So here, that theorem is just an instantiation of that kind of argument. And that's the performance. So we've given some mathematical definition to that boundary. You can ask, well, how well did you do? So we're back to our very simple example, which is perhaps a little unfair to the BC dimension. This is the result that you get. So what is this W0? That's what is it called? I'm just blanking on this. I think that this is just something called the Lambert function. So it's W equals e to the W. Pardon?
W Lambert.
Yes, right. So that's what it is. And how does it look? So the dotted lines here are the VC dimensions. Those are the pack lines. Those are the solid dots, and they're right up at the top. So they're not very predictive. We've drawn lines for different numbers of training samples, and they're quite predictive, even for a small number of training samples. This is a graph for a small amount of noise. This is a graph for a little bit more noise. And they're still pretty good. So here we are. So this is so we've succeeded here in giving some definition to that bound that we believe to be predictive. And I'm done. Thank you very much.
We have time for some questions. There will be microphones around for everybody. So please wait until you have a microphone before you actually ask the question. I think it's great. Any questions? Really? So, yeah, there is surely somebody. Yeah, okay.
Hi, Robert. On?
Jared.
Maybe this isn't on. Ah, here we go. Robert, I was wondering if you could say something about the importance of learning the dimensionality reduction metric that you were speaking about, using learning algorithms as opposed to things like the SVD, and the computational cost associated with that.
So the question is about. Actually, I was not hearing completely well, but I think the question was about the computational cost of learning.
Jared, you have to speak into the microphone properly.
Yeah. Okay. All right. So I think you are. So what I'm doing is I'm asking you enough clarifying questions so that I can find one that I can answer. So I think that there we go. You're asking me about this matrix here, right? And so you're asking me about, all right. Oftentimes, all right, so this answer is a little bit about compressed sensing. And I have to confess that at the beginning that it's a little bit biased. Because oftentimes, in compressed sensing, we take this matrix we generate the matrix by throwing random Gaussians. Why do we do that? Well, I would suggest we do that for the following reason. That in the beginning, with the work of Donahoe and Candes and Tao, we observed that sparsity was really useful. And these guys had a reconstruction algorithm, which was, and that reconstruction algorithm wanted to see a certain kind of structure. It wanted this matrix phi to be an isometry. And once we decided that this matrix had to be an isometry, we then looked around for places that we could prove that it was an isometry. And because we understand how to manipulate Gaussian random variables really well, we gravitated towards Gaussian matrices. Now, so it's nice that we can deal with them, but I wonder if we were to start afresh, whether that's the matrix that we would gravitate towards. I mean, one of the problems with Gaussian matrices is that you have to store all the entries. It'd be much nicer if you had some kind of deterministic matrix where you could calculate these entries on the fly. So that would be much simpler. There are matrices of that form that have very much the same performance as the Gaussian matrices. You can build these matrices out of binary codes using things like second-order Reed-Muller codes. And in some kind of deep way, Matrices that you build in that way are morally Gaussian. They are discrete Gaussians. They're discrete Gaussians because the entries here are like I to the x, p, x transposed, where x is a binary vector, p is a binary matrix, and x is another binary vector. And so they're like Gaussians in that they're quadratic. And they have the same, numerically, they have the same spectral properties. They have fast transforms, because they're like Hadamard matrices. So I think that there are a lot of advantages to using deterministic matrices rather than random Gaussian matrices. Now, I might just be saying that because I'm not as good at manipulating Gaussian random variables as some of my friends.
Are there any other questions or comments? I have one. We learned from the lecture we were at by Andrew Blake some while ago that actually quite often it's very valuable to learn from synthesized data. Mm-hmm. Have you got any practical empirical experiments to show that the right size of empirical data is enough to learn the problems? Would you know how many human beings Andrew would need to make his Xbox work?
It's actually one of the things I would say. I mean, one of the experiences of, I mean, when you're essentially a mathematician or an electrical engineer, and you try to talk to computer science community, then there's a period where you have to learn their language. And our experience to date is that it's a community that is kind of allergic to synthetic data. They don't, I mean, we can make synthetic data, and we get results that we like a lot, but they don't find them convincing. So so I have to confess, we haven't spent as much time on synthetic data as trying to find a sample data set that they will find to their liking.
Okay. And are there any more questions or comments at this point? Can't see any. Okay, so let's thank Robert Calderbank. Great.